Nernst equation. The Nernst equation are particular function extremely important in order to investigate, for instance, corrosion, the way in which a final DDP is generated in a battery, and in general are equations able to characterize and allow us to predict, for instance, obviously with certain degree of approximation, information concerning an electrochemical process. Nernst equations are one of the most important tools that we can have in order to investigate the stability of certain species inside certain specific redox couple. So in general, it's important in order to investigate the thermodynamic of electrochemistry. For instance, one classical example that we will see are the Pourbaix diagram, that are basically designed due to the introductions of Nernst equations solved as particulate functions inside the Pourbaix diagram itself. So now, what is a Nernst equation actually? A Nernst equation is an equation that for a certain specific semi-reaction, a redox couple, for instance a generic semi-reaction like this, the reduction of a metal, the Nernst equation is a function that correlates the open circuit reduction potential as a function of the same value but in standard condition, the temperature and the activity of the species involved inside this semi-reaction. So basically we will see now in a moment the meaning of each of these singles parameters. For instance, the reduction potential, obviously open circuit as this one, in standard condition, it's referred to actually the reduction potential in conditions in which the pH is equal to 0, the temperature is 25 Celsius degree, and the pressure is 1 bar. This concept is extremely important, and it will be extremely important for the descriptions of the Pourbaix diagram. And in particular, we will see later how it's possible to obtain this parameter with the use of a reference electrode. So reference electrodes are always important in order to know the electrode potential, the reducing potential associated with certain specific semi-reactions. And in particular, also, we are able to use a reference electrode in order to extract this value. But now, what is actually the real form of the Nernst equation? Obviously, is a function of this parameter. We have the temperature, we have the reduction potential in standard conditions, and we have the activity. Activity that is basically a sort of reals of concentration describing the reals behavior of species, for instance in solution or just in a solid. Obviously, if we're dealing with a solid, we can imagine the solid as pure, and often the activity in that case is taken as equal to 1. So basically, it's not taken as a real value concerning the presence of impurities, but this is another point. So it's just an assumption. Often when we have a solid or when we have something that is an infinite dilution conditions, the activity could be taken as equal to 1. So now for this specific generic semi-reaction, we know that since this is a chemical reaction, we have a free energy associated, so a variation in the free energy. It could be negative or positives in according if these reactions is spontaneous or not, and this is equal to the one in standard conditions plus RT logarithm of the activity of the product versus the activity of the reagent. So now this is the starting point. This is the equation describing the free energy as a function of the temperature and as a function of the activity, and as a function of something referring to standard conditions, in this case, the free energy. But now, remembering the last video, we have described how basically exists a relationship between the variation of the free energy of Gibbs and the potential. And this relationship is equal to this. For simplicity, we can say that this is equal to this. And in general, we can say that this is equal to this one. So this is the reduction potential in open circuit conditions, and this is the reduction potential in open circuit conditions, but also in standard condition. This is the free energy, the variations of the free energy associated with this reaction development, and this is the same again in standard condition. So now what we can do is introduce this type of parameters here. So we are proceeding with the substitution simply. And we can subdivide each single term for minus mf. And again, minus mf. But this terms is literally, we can say, equal to this. And so we can cancel all this and introduce here the corresponding open circuit reduction potential in standard condition. And here we can make the plus sign and obviously change, for instance, this and this species. What it should be important that trying to extend this final resolution of the Nernst equation in a more generic point of view, we can say that here we can have the productory of each single activity concerning this oxidized species with the corresponding stoichiometric coefficient, and the same for what concerns the activity of the reduced species. So this is the final form of the Nernst equation, an extremely important tool that is able to correlate for a certain specific redox couple, for a certain specific semi-reaction. So this is the one associated, for instance, with this redox couple. For a certain semi-reaction, we can correlate the reduction potential of the open circuit condition with this parameter. Obviously, again, this is the reduction potential in standard conditions connected with the same redox couple. Obviously, we can even introduce, for instance, the activity coefficient directly in these parameters and express the Nernst equation versus the concentration. This is the formal form that is often more useful. So, but now we know that basically this it represents the driving force, the potential associated with a certain type of semi-reaction, defining the tendency of these species to be reduced, for instance, or be oxidized. It's important to remember, and we will see this speaking about the Pourbaix diagram, how higher the potential, higher the tendency to be reduced versus other conditions in which the potential, for instance, is quite low. So when lower the potential, higher the tendency to undergo oxidation. So now it's important to understand how it's possible, for instance, if we want to know this parameter, and we know very well both the temperature and the activity, but this parameter miss, it's important to understand how it's possible to compute the reduction potential in standard conditions. How it's possible. So, if we want to calculate the reduction potential in standard condition, we need to be aware that is an electrode potential. But in one of the first lessons, we have seen basically how it's impossible to measure a single electrode potential or directly. Because the only one type of measurement that we can do is a potential difference. But how it's possible to know this parameter if we are only able to know a potential difference? But to know this parameter is crucial, because we need to know this parameter, we need to know the temperature and even the activity in order to predict what it could be, for instance, the pathway of the potentials versus maybe the pH in the Courbet diagram. This concept it will be more clear speaking about Courbet diagrams. So how it's possible to know this parameter? The reduction potential in standard condition. So, the reduction potential in standard condition could be known taking in advantage of a reference electrode. First, what is a reference electrode? A reference electrode is an electrode that is always present in a cell in order to know and understand the electrode potentials of the working electrode and the counter electrode. So in a cell, basically, the main component together with the electrolyte are the working electrode and the counter electrode. And this is the electrolyte. So basically, in this case, if we are imagining now, maybe, that we want in an electrolytic cell apply with a potentiometer, this instrument, a certain potential difference, maybe we want to apply a potential difference between the two electrodes that is equal to 2 volts. We want to apply something here, this difference, it should be 2 volts. So we are taking our potentiometer, we are clipping one electrode, we are clipping the other one, and we are promoting, for instance, the generations of current in order to induce a polarization here and a positive polarization here, in order to create a potential difference between these two electrodes equal to 2 volts. In this case, this is an electrolytic cell, so we are inducing a polarization. We are not obtaining a spontaneous potential difference due to a reaction development, as in this case of a galvanic cell. No, here in an electrolytic cell, we want to induce a potential difference that is tuned by the potentiometer, the instrument. But, okay, we are applying 2 voltage, but the instrument, how can be able to understand the electrode potential? Let's make an example. We know that we are applying 2 volts as a potential difference, and the instrument can do that. But this difference, it could be maybe a difference between the potential of the working electrode that is, so this could be even something like this, so in order to be more clear. But maybe the potentials of the working electrode, it could be 200 volts, and the potentials of the counter electrode, it could be 202 volts. Something like this, or the opposites, since the electrons are moving toward this direction. And so we have that we are applying a potential difference, and we have the difference between the working electrode potentials and the counter electrode potential that is actually 2. But maybe the same result is referring to a situation in which this is maybe 4 volts and this is 2. So the difference is always in this case 2, and also in this case, but we can understand how it's really, really different. Here we have a huge polarization, and also here, but the same difference is quite pure. Here we have the same difference, but a really small polarization here and the polarization here. So the difference that we have tuned is the same, but the situation is completely different. So how we can be able to understand exactly what is the value of the electrode potential? So how we can understand if you are in this situation maybe or in this situation? We need to introduce a reference electrode. A reference electrode allows us to understand not the potential difference. We already know the potential difference, but the electrode allows us to understand the single electrode potential. In which way? So we have, for instance, always a 3-electrode system, the reference electrode. Introducing the reference electrode here, we are able to know if we are in these situations or in this situation. Before starting speaking about the working principle of a reference electrode, it's important to know that inside here, in the circuit connecting the reference electrode to the original one, we have a huge resistance. Why? Because obviously we need to close the circuit and connect the reference electrode to the starting circuit. But we need to ensure a flowing of electron in an extremely pure way, because in this way we are not generate any types of perturbation. So how actually a working electrode works, and so how actually a reference electrode works, and how a reference electrode is able to allow us to determine this parameter fundamental for the resolutions of the Nernst equation. So, reference electrode, let's make an example of reference electrode. For instance, one type of reference electrode is the natural or normal hydrogen electrode. First, let's look at the structure of this electrode. So this electrode is composed in this way. So we have a platinum wire with a platinum plate here, acting as a current collector, and we have an electrode here, a glass electrode, in which we are flowing inside some molecular hydrogen that is entering here and it's escaping here, and we are putting this inside an acid solution. So we have H+, 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 and the connected bubble of hydrogen. Why? Why we have hydrogen, molecular hydrogen, and H+? Because this electrode is based on a specific semi-reaction, a specific redox couple. And this redox couple is H+, H2. So each single electrode is basically based on a redox reaction, exactly as a convection electrode. A convection electrode is a place in which a semi-reaction associated with a certain redox couple is proceeding. The same for what concerns a reference electrode. Also, reference electrodes are based on specific semi-reaction. And in the case of a natural hydrogen electrode, this semi-reaction is H+, plus one electron, giving this. This is the specific semi-reaction. And so we need to have both hydrogen and both H+. And this is basically just the current collector that is able to ensure the flowings of electron in this direction, or in the opposite. So basically, this is the structure, and this is the reaction on which this electrode is based. But what is the working principle? So we know that basically it's impossible to measure a single electrode potential. We can only measure a potential difference. And so, even if we are introducing a reference electrode, how it's possible to measure a potential difference? How it's possible to measure not a potential difference, but an electrode potential? So, make here our well-known design. In this case, with, for instance, the reference electrode. So we have here the working electrode, the counter electrode, and the reference electrode. So we have described previously how it's possible to know the potential difference between this electrode and this electrode, but it's impossible without the reference electrode to know the single electrode potential. Well, if we introduce here a reference electrode, well, also in this case, it's impossible to know directly electrode potential. But what we can do is measure a potential difference. And in this case, the potential difference that we can measure maybe is the potential difference between the working electrode and the reference electrode. So we know, remembering the previous situation, that the potential difference between the working electrode and the counter electrode is 2 volts. So the total potential difference is between this one and this one is 2 volts. But we want to know the potentials of this electrode and the potentials of this electrode. What a reference electrode allows us to do in a smart way is to measure the potential difference between the working electrode and the reference electrode. Since the potential difference could be measured, but we can assume with an assumption that the reference electrode is characterized with a certain already known electrode potential. And so the electrode potentials, for instance, if you are in standard condition of this semi-reaction, the reduction potential of this semi-reaction in certain conditions is equal to 0 volt. But how we can know this? How we can know that this electrode potential is 0 volt in standard conditions if we are not able to measure it? We are make a decision. And this decision is an assumption. We're assuming that this is a reference value. We are saying, okay, this value has this specific voltage. Always in certain condition. Always we are choosing this as a reference value. And so what does it mean? That if we know that this is 0, because it's an assumption, we can measure the difference between these one. But the difference between something and 0 is something. And so we can measure the difference, but we know that this difference is exactly equal to the electrode potentials of the working electrode. And so, for instance, if this is minus 2, we can measure the potential difference, and this potential difference is maybe 2 volts. Maybe this is minus 2. And so it could be possible to know first this electrode potential and then even this one. Because we know the total potential difference and we know this potential difference. Due to this potential difference and the reference value, we can know this working electrode potential, and know the total potential difference. From this value, we can even reach this one. And this is extremely important because it allows us to understand in which way the natural hydrogen electrode works. In particular, if we want to understand better, we can couple, for instance, an electrode of a certain specific metal, maybe, with our hydrogen electrode. So this is our natural hydrogen electrode, and this is a classic electrode, a working electrode. So we want to know, we are for a moment imagining to avoid the presence of a counter electrode, we want to know this potential. What is important to say is that we know that maybe if we are in standard condition, the pH is equal to 0, the temperature is 25 Celsius degree, and the pressure is 1 bar. What is happening is that in this condition, this electrode potential, the reference electrode potential, is, we know, as a convention, equal to 0 volt. And this one is unknown. we can use a voltmeter and we can measure the final potential difference. And we know that it's basically 2 volts. So we know that is a potential difference, but we know that this is 0. And so the difference between 2 and 0 is 2. And so one important thing could be, okay, we know that this is the potential difference, we know the reference value because we have assumed this as a reference value universally accepted, and so this it could be 2 volts. But this is not finished. Why? Because this it could be plus 2 volts or minus 2 volts. So this, it could be more positively polarized or more negative polarized. The difference is always 2, but how we can say if this is equal to 2 or minus 2, the difference is always 2? Well, we can understand this in accordance with the flow of electrons. Why? Because remembering that electrons want always to follow higher potential, if when we are coupling an electrode, a natural hydrogen electrode, with a certain generic working electrode, if the flow of electrons follow this direction, and so this species is reduced and the hydrogen is oxidized, well, in this situation, basically, we can say that this potential it will be higher, and so we are in this situation. But from the other hand, if we are coupling maybe another type of working electrode made of another material, and we can appreciate a flow of electron in this direction, the opposite one, and so is proceeding the reductions of hydrogen and the oxidations of the metal, this means that this starting point, it will be characterized with a smaller potential, and so this is minus. So the numeric value is due to the potential difference, since this is 0 as a reference. But the sense is in accordance with the directions of the electrons. So we can have the flowing in these directions or in this direction. For instance, if we want to make this more clear by looking at a reaction, if this is, for instance, the reaction of hydrogen, this is a reduction, so we are proceeding toward a reduction. Electrons are collected in order to reduce H+, and this is the metal that is oxidizing in order to release, for instance, electrons. And so in this case, this potential is smaller, and this is minus 2, the working electrode potential. From the other hand, if the reaction is proceeding in the opposite direction, so here we have a reduction, oxidation, and here we have a reduction, we have an opposite flow of electrons. This means that the difference is always 2, but this potential is higher, and so this is 2 volts and not minus 2. We can even have different types of reference electrode. One of the most stable is the calomel electrode, that is based on another different steps of reaction. Obviously the reference values, it will be different in the calomel, but the concept is basically the same.